Line L1, we're going to take a look at a bunch of review stuff. This is not part of your second year materials. This is simply placed inside here for you to be able to bring yourself up to speed. Maybe you did cover some of this material inside of level 1. Maybe you did not cover it. So this is an optional one. If you want, skip ahead to the first video that you're going to go and have. All right, for the review over here, the purpose of grounding and bonding is to prevent fire and shock hazards. And inside of the Canadian Electrical Code, one of the big things that we want to do is we want to prevent electrical shock to humans. So Rule 2, Buck 10 is going to go and tell us that a human should not be exposed inside of a dwelling unit to more than 150 volts above ground. And over here we see that, we want to use 122 40-volt systems. So where we would ground the system would make a difference. This one over here, we would see that line 2 would be at 0 volts. They could touch line 2 safely, but if they touched the neutral, that would be 120 volts above it. If they touched line 1, that would be 240 volts above it. So there's danger over there, right? That 240 volt shock. Same with this one. If we grounded the other line, we would be able to get 240 off of that line, right? Just standing still with our human at ground potential over there. Our safest situation is to ground the neutral point of the transformer. When that is done, then what we would have is they would have no more than 120 to this one and 120 to this one. 1200 I wrote there. Yet we would still be able to go and get 240 across from line to line. It is very rare that somebody will get a 240 volt shock. You'll hear people be like, oh yeah, I got a 240 volt shock. Probably they didn't. They might have gotten a shock off of a single leg down a piece of equipment that was connected to 240. But in order to get a 240 volt shock, you would have to have somebody that would be isolated from ground. So we will float this dude. We'll place him on a little rubber mat there. So he's isolated from ground. And the dude himself would have to go and touch with one arm, line 2, hold on to that. And then with the other arm, touch to line 1, and the rest of the body would have to be isolated from ground. At that point, they could actually get 240. But in most cases, most shocks that most of us receive are 120 volts. This is why most of us, well, actually all of us, if we're listening to this, are survivors of electrical shock. And I don't know if you've all been shocked, but I have been shocked from just sloppy work habits in the past. The review section goes over top of the purpose of the ground is not only just to go and minimize the potential voltage that we're going to be exposed to, it's also to go and help my overcurrent devices or my circuit breakers to go and operate, or my fuses, whatever I have inside of there. Over here they're showing an ungrounded system. If that ungrounded system has a fault off of it, there is no place for fault currents itself to flow. So if there's no place for fault current to flow, what we end up having happen is that that system, which would have been a floating or an ungrounded system, is just going to idle along. There's not going to be any difference other than we're going to see, different voltages across 0, 120, or 240. What we would have to wait for is we would have to wait for a second fault, that one over there, that would then be able to complete this path. And at that point, we're going to have a complete path for current flow through our transformers. And because the path itself is going to be low impedance, I is equal to E over top of R, we would get a fairly large amount of current that's going to flow, right? 240 volts over top of, let's go and say 2 ohms of resistance over there. So we'd have like 120 amps. Should be enough that it's going to go kick out one, if not both, of these instantaneously. Well, close to instantaneous. Depends on the response curve. Obviously, this waiting for us to have one fault and then waiting for us to have another fault is problematic. We don't want to go and have that, so that's why we start with that central solid ground that we have on the system. That way, by us having this thing centrally and solidly grounded over here, we have now got a path that is going to lead back to the neutral. Remember that current itself wants to always return back to the neutral. So if I end up with a fault, here's a live line that faults down to, we refer to it as ground, but in most cases it faults down to something that's bonded. The bulk of my current is going to go and travel back along the bonded pathway. That's going to be the bare copper conductor, the conduit sheaths and stuff like that. That all travels back to my neutral bus, which is tied to the panel, which is then going to go and allow us to go and complete that circuit, to deliver it back to the transformer and in. That is ultimately the purpose of that bond strap and bond screw connection, is to go and deliver fault current back to the neutral itself. So we see we got a complete path. Once again, I is equal to E over top of R. The bulk of my current travels along this path over here, and only a tiny little bit of current will travel through the actual dirt itself and the earth all the way back out to either my supply ground of the transformer or my ground that I have at the panel. wherever those grounds would be. But the bulk stays on the bonding path. We are supposed to go and make sure that our bonding path is going to be low impedance. Inside of BC here, we're actually supposed to go and make sure that whatever our bonding path resistance is going to be, it should be such that it's going to develop 5 times the protection current. So if I've got a 15 amp circuit, I need to go and have protection, or I need to go and have a bonding circuit for a 15 amp that is going to go and be low enough of an impedance that I'm going to be able to get 5 times that value over there. So you just take 15 times 5, that's going to go and get you to 75, so I need to have 75 amps that would flow off of that one during the fall. If I've got 75 amps, then I can go and figure that out as far as my value of resistance. R is equal to E over top of I. So take 120 volts on that circuit over top of 75 amps. That is going to go and get you to your value of resistance. It's going to be, about a little less than 2, maybe 1.6, 1.8. Okay. Types of grounds. We're going to have grounds that have to be applied onto a system neutral itself. BC Hydro is usually going to go and take care of their grounding at the transformers. We're only required to ground where we receive power into the building. So BC Hydro will take care of any grounding at the transformers if necessary. This ground is not always necessary. And it is an incomplete drawing in the fact that, I don't have the primary of the transformer. That would be this over here attached to the high voltage lug over there. We don't have that drawn into the transformer there. We're only showing the secondary side, but you can see it's a 12240 type of winding, and that I've got my, what we refer to as identified conductor that is going to be connected to the center part, and that you can see this thick cable over here would be BC Hydro's cable that would be going down to the ground. It's going to be a system ground that would be provided by them. Disregard these, CEC rules inside of here. Unfortunately, this thing was written back when we were still operating underneath the 2015 Canadian Electrical Code. And then, actually, the whole module over here was written by me when we were under the 2015 code. I wrote, I illustrated. Then we had the 2018 code that came out and had completely different changes to it. They redid Section 10. I'm going to identify those as we go along. But at that point, I was covering electronics for the university for 2 years until they could find somebody for that. So I wasn't there to go and update. So now that I'm back in, I'm going to have to go and rewrite this one, as I'm reading through it, prepping for class over here. I'm really seeing a lot of places where that code needs to be updated. I'll identify those as we go along. This ground, though, will not be your problem to go and put in. If they're putting up a pole-top transformer, they will take care of that. And then that ground is going to be taken care of by them at our service for a standard 12240 volt system. We are going to go and have our weather head. It could be coming in underground as well, but we're going to have a meter base, and then from the meter base, we come into our panel. Inside of the panel, we need to go and ground down at our neutral. Do note as well that we do have the bond strap that is going to be inside of there as well, because the bond strap will deliver the current back to the neutral itself. We will have our electrode, that's going to be rods or a plate that's going to be buried in the ground. And we are going to make sure that the first point of connection is always going to be there at the neutral. Meaning when we take this bond wire into the panel, it needs to be taped off so it's not making contact with the side of that. Equipment grounds are going to happen inside of third year. You have not covered these, but we do have some systems that don't have a neutral to them. They're going to be three-phase systems referred to as delta. At that point, we do still have to have a ground on the system just to surround everything and provide a fault path back, but it's not going to be tied to a neutral. We just refer to that as a equipment ground. Bonding is going to be the process of connecting all metallic components together so that there will be a path for current to go and flow. You've seen this illustration before, illustrating how we get current from our transformer. So our transformer is going to feed down through lines, down through into the bus bar over here. It is then going to go and feed into my panel. From my panel, it is then going to feed through into my sub-panel. From my sub-panel, we are then going to go and carry that current down my conductor. And right over there, we see where that conductor has made contact with the side of the box there. And what we will have then is we will have a return current that's going to happen. The current's going to travel back along the box, up through the nipple, across the panel. The panel is going to be metallic. It is then going to go to the bonding lug that's going to be inside of the panel, which has got a bonding connector. There'll be a green connector run through this PVC. It says that there's a bond inside of there. So it's going to run back along the bond to the bond lugs inside of this panel, travel through the case of this panel, travel up the bond strap back to the neutral and then travel from the neutral back up the neutral conductor and all the way through to my transformer. Current forms complete loops, right? It's going to go and have to return back to the transformer. That's where it wants to go. And we see in this case, absolutely nothing is flowing up the actual grounding conductor itself, that one that's over there. It is going to carry a lot of current. This one over here, we see that under faults, it carries nothing. That's why we're getting away with a number 6. We'll talk about that a little bit later on. But this one over here is going to be carrying a large amount of fault, right? We got 100 amps is what we have got for this breaker over here. This one here might be it is a 200 amp over there. This one's 100 amp, and so we've got a large amount of fault current that could travel through. So that bond is going to be sized large enough that it could deliver back all of the fault current for that 100 amp over there. Last little thing to go and review is that we have got other sections that are going to need to be bonded down inside of structures. These are going to be metallic components. Different types of buildings have different requirements. We will talk about some to do with livestock, which is a very big deal out here in the Fraser Valley later on. But for any general one, we need to go and bond down a couple of things. Metallic gas lines, where the metal gas line comes in. Past that, it should be the gas fitter keeping everything bonded together. We're also going to go and have, if we have any metal sewer lines coming in. We don't have a lot of that, but if so, we would have to bond that. Same if we have metal water pipes that would be coming in, we would need to bond those down. You can see that each of these is going to have a conductor coming from a strap on that device that is going to be tied back to my main grounding conductor over here. We are actually allowed to bond them to the ground itself. The other ones that you should be familiar with are going to be my TV boxes and my telephone boxes. Telebox from BC Tel, Shaw boxes, any of those other ones that are going to be considered to be your cat TV. These ones are not going to be found rules inside of Section 10, but you're going to find the rules for this inside of Section 54, which is going to be dealing with TVs and community antenna distribution. That's CATV. And these are going to be inside of 60, which is going to be your electrical communications types of circuits. Once again, what we find inside of the code book, by the way, is going to be a minimum standard. What you discover inside of 54 and 60 will be very small sizes of wire that are going to be required to go and bond these components that are going to be inside of there, blocking devices. What you will get in your spec sheet from BC, or from TELUS or from Shaw or whoever it's going to be, is going to be oversized to that. They do want a larger conductor just for the sake that it is going to be guaranteed to be, a better connection and less likely to be damaged, etc. All right, that is our quick little review. Let's talk about the main material now.